Good afternoon. We're going to finish up our solubility questions, starting with number 7. Okay, so all of these reactions involve ionic compounds, and when you combine two aqueous ionic compounds, you're going to get a double displacement reaction. So the cobalt will go with the hydroxide, and you get COOH2. Because the cobalt has two nitrates, each nitrate is -1, you know it's cobalt 2+. All right. And the sodium goes with the nitrate. Okay, and we need 2 of these. And we will form 2 of these to balance the equation out. Silver and potassium switch places. Silver chromate, you need 2 of those. Plus potassium nitrate, and you will need 2 of these, and you will form 2 of these. Calcium and potassium switch places, you get calcium sulfate plus potassium hydroxide, 2, and that is balanced. The ammonium and the sodium are going to switch places because those are the positive ions, so the NH4 will go with the hydroxide, and the sodium will go with the chloride. The barium will switch places with the hydrogen ions and form barium sulfate. The hydrogen then goes with the chloride, and you need 2 of these. All right, NaNO3 and PbI2, and then the H and the Na will switch, and H and OH neutralizes to give us H2O liquid plus NaCl. Okay, so I did not do the states of matter because number 8, we're going to go back and we're going to add solid to anything that's insoluble, and we can add aqueous at that time to the things that are not soluble. So we're going to be using our solubility rules, our NAG/SAG, and our Castro-Bear to figure out which things are soluble, and things that are not soluble are going to be solids, and they're going to precipitate out. So cobalt hydroxides, most hydroxides are going to be insoluble, so this is going to be a solid, and I did not leave room for that, so that's S. Sodium and nitrate both are on the soluble list for group 1 and nitrate, so that's going to be aqueous. Silver chromate. Silver is usually insoluble, and definitely with chromate it's going to be a solid precipitate. Potassium and nitrate is aqueous because we have a group 1 and we have a nitrate. Most calcium things, Castro-Bear, those are going to be solid unless it's with nitrate. And this is a strong base, ionizes completely, so we know that it's aqueous. Ammonium is on our NAG/SAG, so that's going to be aqueous. NaCl, that's table salt, we know that is going to dissolve, so that's aqueous, so there is no precipitate in this reaction. In other words, these all stay as ions, so there really is no reaction going on. Okay, barium sulfate, that is going to be barium with sulfate insoluble, so that's going to be a solid. Okay, part of our Castro-Bear again. And HCl is a strong acid, which will ionize completely. Sodium nitrate is aqueous. Lead iodide. Lead is on the PMS list for lead, mercury, and silver, and this is a bright yellow precipitate that when you mix these two clear solutions together, just forgot the AQ over here, AQ, you're going to get that bright yellow solid. Okay, and NaCl, that's salt, that's aqueous. So we have double displacement because these are all ionic things combining. We have 2 ionic compounds in aqueous solution combining, and then we go back and we figure out from our NAG/SAG rules what things are aqueous, and Castro-Bear tells us what things are usually going to be solids. All right, number 9. Number 9 is a doozy. So we have a 500 milliliter solution of that concentration iron nitrate. It is added to 250 of 3.0 times 10 to the negative 4th molar NaOH. Will it precipitate form? So we are going to write out the reaction that is taking place here. We have iron nitrate. Is it iron 3 nitrate? It is, so this is a 3. Iron 3 nitrate, aqueous, is going to react with the sodium hydroxide, which is also aqueous since it's a strong base, and it will form FeOH3, which is a hydroxide. Those, if it's not on our strong base, it's usually not soluble, so that's going to be a solid, but only some of it will form. And the other product is our sodium nitrate, NaNO3. I will need 3 of these and 3 of these to balance the equation. Okay. So we need to figure out if the concentration of my solid that forms is going to be big enough to give us a Q value. Remember, Q is the reaction quotient, and if Q is bigger than the KSP, then you will get a precipitate forming. Okay, so we need to find Q, which is just like finding K. So we're going to have products over reactants. And so we need the KSP for the reaction. The KSP for iron hydroxide, we would have to look up, we would have to be given that information. It is 6.3 times 10 to the negative 38th power. That is a tiny number, so very little of it is going to actually form. And remember, the KSP is going to be this solid actually breaking apart into Fe3 plus and OH minus. These are concentrations of the aqueous solution. So iron ions that are forming, the hydroxide ions that are forming from this solid, it's going to give us a KSP of that. Okay, remember, we don't include the solid in the KSP. It would be over the reactant, which when we're looking at this guy dissolving, this is the reactant, and the product is Fe3 plus and OH minus. Okay. So what is our concentration of Fe3 plus? What is our concentration of OH minus in the reaction that it's describing up here? We need our total volume, 750 milliliters is the total volume because we're adding 500 and 250. And in liters, we move the decimal 3 places. We get 0.75 liters of solution total. Okay, how much of the Fe3 plus do we have? That is kind of a stoichiometry problem. So we added 0.5 liters, that's this 500 milliliters, of this concentration, 4.1 times 10 to the negative 4th moles per liter, and that's going to tell us how many moles, 2.05 times 10 to the negative 4th. moles of Fe3 plus are in our combined solution. How much hydroxide is in there? Well, whoops, sorry about that. I added 250 liters of 3.0 times 10 to the negative fourth moles per liter. Remember, this capital M is moles per liter. Write it out so you can cancel the units and know that you did it correctly. And that's going to give us 7.5 times 10 to the negative fifth moles of NaOH, which is a strong base, which means it's going to ionize completely into Na plus and OH minus, so that's how much hydroxide we have. Okay, so we know how much is in our total solution now. So to find the concentration of these, it's going to be the moles that we added divided by the total liters. So we're going to have 2.05 times 10 to the negative fourth moles divided by the 0.75 liters, because that's our new volume, and this is the concentration of our Fe3 plus equals, and that is going to be 2.73 times 10 to the negative fourth molar Fe3 plus. Concentration of OH minus, that is not, OH minus is going to be our 7.5 times 10 to the negative fifth moles per 0.75 liters. That's going to be 1 times 10 to the negative fourth molar. So you can maybe already see that when we do Fe3 plus's concentration times hydroxide, even though it's cubed, this KSP is very small. So we're going to get a Q that is larger than the KSP, but let's go ahead and finish the problem out. So we have Q, which is just like our K, our equilibrium constant, products over reactants. It's going to be Fe3 plus, but it's not at an equilibrium. OH minus cubed, and plug in our values. 10 to the negative fourth molar times hydroxide, 1.0 times 10 to the negative fourth molar cubed, and that is going to be 2.7 times 10 to the negative 16th. And Q, this value, is definitely greater than KSP. Therefore, a precipitate will form. Okay, and that is our answer right there. All right, so the second part, part B, we have a solution containing lead 2 nitrate is mixed with one containing sodium bromide to form a solution that is 0.015 molar in lead 2. So they are giving us the concentration of lead 2 nitrate, and sodium bromide does a precipitate form. This is actually an easier problem. We don't have to figure out as much, and I do not have room, so let's move over to here. Okay. So we want to know, does a precipitate form? Lead 2, Pb, 2 plus nitrate, NO3. You need 2 of those. That's going to be an aqueous solution because it's a nitrate. Mixed with sodium bromide. That's a group 1 with a halogen. That's going to be aqueous. And we want to know, we know NaNO3 forms, aqueous, and I will need 2 of these and 2 of these. This lead bromide solid, do I have enough of these ions to give me some solid product? Let's see if I can shift this over so you can see it. Okay, do I have enough to give me that solid? Let's see. KSP for our lead bromide is going to be lead, Pb2 plus times bromide, negative, and square that one. And the value, which we would be given, is going to be this. So let's do our Q, since it's not at equilibrium, and they gave us the concentration of 0.015 molar for our lead nitrate, and the sodium bromide concentration was 0.035 molar squared. So if I do that, I get 1.84 times 10 to the negative 7th. Comparing these two, our Q is less than the KSP value. Q is less than KSP, therefore no precipitate will form. Okay, no precipitate will form. And that is our answer.